Okay. So before moving forward with rainfall runoff, I would like to make some very simple experiment with R and random numbers. So just 1 second, I start the session. Here I am. First of all, let me generate random numbers, because in order to play with numbers, I need a time series. I could use a time series is a series of observations depending on time, like rainfall that we used to calibrate the rainfall runoff model or the river flow. And the problem when using observed data is that these data usually are not extended much. In this case, we have some reasonably long time series, because we have 3,650 data, but I would like to play with some longer series. So it's better if I generate a random series from R. And to generate a random series, basically, you need to specify the underlying probability distribution. We learned yesterday that there are probability distributions which describe the cumulative probability or the probability density of the data. And these are very useful because through an analytical relationship, depending on the value of the data of the river flow, for instance, you can compute the probability. These probability distributions can also be used to generate random numbers, because basically once that you specify the shape of a probability distribution, the probability distribution, again, what is this? It's a relationship which relates the data with their probability. You can also use this relationship to relate the probability with the data, which means that if you randomly specify probabilities, you can compute the related data, therefore generating synthetic data. Basically, the probability distribution is something that you can write in this way. For instance, for the cumulative probability, PDX is a function of x. And then you can compute, you can take the inverse of this distribution. So you can write that x is equal to f minus 1 of p dx. This is very useful because, it's useful to compute the probability of the data, but it's also very useful to compute the data depending on their probability. Let's suppose that you want to estimate, for instance, the extreme value of a given process. Therefore, what you do is to take the inverse of the probability distribution, and then you fix a very small probability of exceedance, and then you compute the extreme value. And the same for droughts. If you want to estimate the very extreme low value of flows, you fix here a very small probability of not exceedance. Let me think if I said it correctly, because it's very low, so you have a very high probability of exceedance, so a very small probability of not exceedance, and then you compute the low flow. So these are very useful for that. And another very useful application of the inverse of the probability distribution is that if you put probabilities here, randomly generated, you can generate synthetic data from the probability distribution. And for instance, I could put here increasing probabilities of not exceedance from 0 to 1, equally spaced, and then I compute the related data. So they are very useful also for generating synthetic data. And you can do that in R. We will study in detail how this performs. For now, let's take for true that with R, you can generate X from a given probability distribution. So you specify the probability distribution, and R can give you observations, values of X from that probability distribution. So let's take it for true now, and then we will see in more details in the next lectures how it works. Okay? So, of course you have to specify to R the probability distribution, but not only the probability distribution, also the number of data that you want to generate. So let me use a name for a variable like synthetic, synt, equal to, this is going to be a vector, sorry, I increase. This is going to be a vector. So synthetic is equal to, R norm is the function for generating data from a normal probability distribution. It's called R norm because it means random from normal. So R norm, let me put 10,000, which is the number of data that I want to generate. And then I have to specify the shape of the probability distribution. I already specified that it's a normal distribution, but you remember that the normal distribution has two parameters, and in order to identify the detailed shape of the normal distribution, I have to specify these two parameters. And you may remember that the first parameter is the mean value, the average. The second parameter is the standard deviation. So let me use 0 for the mean value and 1 for the standard deviation. This particular probability distribution, the normal distribution, with mean 0 and the standard deviation 1, it's also called the canonical normal distribution or standard normal distribution. It doesn't matter here what values I select for 0 and 1, you could take whatever. But let me start with this. So, in a very simple way, I generated these random numbers. And let me show you how they behave. Let's take a plot. So, plot synt type equal to line. You see the plot here. And what you immediately see is that most of the numbers are very close to the average, to the mean. You see that the mean is at 0, clearly, because we specified the mean at 0. And you see that most of the data are included within the range -2 plus 2, which means minus 2 standard deviation plus 2 standard deviation. Is this true? Let's try to generate another normal distribution with different mean and different standard deviation. So let me do another generation with mean 100 and the standard deviation 10, or let me say 5. Okay? And let's plot it again. Let's see the plot. Now, you see that the mean is around 100, of course, and you see that most of the data are within the range 90-110, which means mean plus minus 2 standard deviations, again. This is striking, let's say, a behavior of the normal distribution. It can be proved that 95% of the data are within the interval mean plus minus 1.96 sigma. These are 95% of the data. This can be proved. It's not interesting for us to prove it, but it's interesting to notice that. Okay, now let me go back for practicality to the previous situation in which the mean is 0 and the standard deviation is 1. Here is the other graph. I made another generation of random numbers, so this is not the same series that I had before. You may also want to see in more detail how it behaves. So if you want to see in more detail, let's plot from 1 to 100. The Because, you know, if you plot 10,000 data, you don't see anything. But if you plot from 1 to 100, you see with more detail. And please note one thing of these random numbers. One thing that probably is not very significant for you now, but you should keep it in mind. You see that there is no relationship between subsequent values. They are drawn from the distribution independently. So you may have up and down randomly. Okay, there is no relationship between one value and the subsequent one. Something that, you know, in river flows is not really represented, not really realistic. Because in river flows, you have a dependence. If you go to the Po River and you see the river flow today, you don't expect tomorrow to find a very different situation. More or less, the river remembers its past. I say more or less because it depends on the river, of course. But huge rivers, you can understand that they remember their past. So this, you know, this time series which I generated is not really representative of river flows. So this is something that you have to keep in mind, and then we come back to it on Monday. Okay, now a question is, what is the probability density of this series of data? Of course it's Gaussian, because we know it. This is an advantage, because an advantage of generating data, of working with synthetic data, is that you preliminarily know everything of the data. In this case, all that you need to know, all that you can know, is that they come from a Gaussian distribution, they are independent, and the parameters are mean 0, standard deviation 1. But this is a big advantage. You already know what's going on, okay? But let's suppose that we don't know, and we wonder what is the probability density of this data. So let's try to draw it as we learned yesterday. And I told you that, you know, one way of doing that is to split the range of definition of the variable in segments and count the number of observations that fall within each segment. This is still not probability density. It's just probability of each observation to fall into each segment. And then you remember that if one wanted to estimate the probability density, you just have to divide for the width of the segment. So now let's start by counting the observations that are within each segment. And you know, here the range, let's compute the minimum and the maximum. Min, sin is minus 4, 3, 7. The max, given that it's symmetric, you expect that the max is more or less similar. 3, 6, 3 is more or less similar. So we should start from minus 4.5 and end with, for symmetry, plus 4.5, which means some 20, more or less, no, let me say, if we want to take like some 20 intervals in order to get a meaningful picture, I should take a width of the segment equal to 0.5. Okay, that's fine. So now I have to count how many observations are lying within each segment, starting from the segment between minus 4.5 and minus 4. Okay, it's clear? Okay, let's count it. And let me define first of all a vector where I will store the number of observations in each segment. The segments are, I think they are, if I start from minus 4.5, I think they are 18. Let me start with 18. So let me define, not really dense, but proper, equal. Let me define a vector repetition, 0, 18. This is a vector of 18 zeros. If you visualize it, you see 18 zeros. Now I have to fill the vector with the count of the number of observations that fall within each segment. If you don't understand, just stop me. It's a conversation, okay? Don't be concerned. So let me say that prob 1 is equal to, how can I count the number of observations in the range minus 4.5 minus 4? I have an idea, let's see if it works. Length Sint, but not the overall length of Sint, because it's 10,000, I know it. I have to specify that Sint should be greater than minus 4.5, and again Sint less than minus 4. I'm not sure if this works. I make a try. Let me see. What is prob 1? Could be. It means that there is just one observation in the range. So please be careful of the syntax that I used. Okay? Basically, you see that I put the name of the vector, Sint, followed by two conditions between square parentheses. And the conditions operate a selection of the elements of the vector. Look, let's try to do this. This would just display, can you see it? It's still in the low part of the screen, you can see it, okay? This will just display the observations falling in that interval. No, there is something which is... One second, because I wanna make sure. Okay, I think I made a mistake. Let me... I am starting again, because maybe you understood the mistake that I did. I didn't understand. So let me start again. And let me see the minimum first of all. Okay, now the minimum is 3 point. Okay, so now we have to modify slightly. Minus 4 plus 4, so it's 16. I redefine the vector. And now let me see if it works. No, there is something here which... There is something in the syntax that is wrong, so let me make another experiment. I will converge quickly, but let me make a couple of experiments, because it's the syntax for the selection which is not correct. Okay, this is fine. And this is fine, okay. Okay, now this works, so let me see. Oh, sorry. No. Okay, I understand. The problem is the minus sign. Let me make it again. Yes, okay. The problem was, I tell you, the problem was this instruction here, because the minor followed by a minus sign is synonym of an equal in R. So I should have put a parenthesis here, and I want just to explain better. In R, if I write A10 and then A, you see it's a synonym for an assignation. The minor sign followed by a minus sign in R is a synonym for equal. So basically, you have to be very careful. And when you want to write minor of minus something, you have to put the square parenthesis before the minus sign. So this was my problem, which I didn't use it. And this is subtle, you know, and it's something that you have to keep in mind. So I'm starting again from the beginning. Sorry for that. And I need the minimum and the maximum of this vector, minus 4.30. And the maximum is 360. Again, I have to start from minus 4.5 to plus 4.5 to draw the density of this vector. So I define now, again, the vector with a dimension of 18. That's fine. And now let me try to isolate the observations here that are greater than minus 4.5 and lower than minus 4. Now it should work. Okay, now it's working. And then I can redefine my probe 1. Here. The only thing I have to put a square parenthesis here. Okay, now should be working. Let me make a check again on the length of sync. Yes, it's still there. Okay, so basically the first element of the vector probe is the number of observations that fall between minus 4.5 and minus 4, which is 1. Now let's move forward with the second observation of the second element of the vector probe. And I should collect the observation between minus 4 and minus 3.5. Of course, I could write a fourth cycle to perform this computation. I don't want to do that because I want to make it step by step in order to be clear. And you see that the number of observations falling in the second interval is increased, as you would expect. Now I have to quickly move forward because I have 18 of these operations to compute. So minus 3.5, minus 3. Look, you may say that I may miss some observations in this way because I would need an equal sign at the extreme of the interval, one of the two extremes. But given that I'm dealing with real numbers, I can use the minor and the major without the equal because it's impossible to get a real number that is strictly equal to the integers or half integers that I am specifying. So it's not needed. I move forward quickly. Actually, I needed just 17 observations, but this is not a problem. Now, let me take the sum of probe, should be 10,000. There is something which is wrong here. Let me see. It is wrong when it became positive. Okay, let me see. Still okay. Just 1 second, I'm checking that the time series is still okay. Yes, it's okay. So let me see where is the mistake. Can't understand why. Let me okay. It's the order of, because it matters, the order in which you make a selection it matters, because it operates first the selection, I think, on the first, and then the selection on the second. So basically, if I make first the selection sigma greater than 4, it's 0. Okay, so let's repeat. So far it's fine, I would say. And let me see if it is fine. Okay. Okay, let's try to do it this way. Sorry. Instead of putting the two conditions in sequence, let's put the two conditions in this way, because it means that they should be both satisfied. Because if you put them in sequence as I put before, I still have not very clear what he did, but in any case it was not correct. So let me do it this way. And let me, sorry for that, repeat. Okay, I move forward quickly. Hopefully it will work. Okay. Okay, now let me see if it is correct. Okay, now it's correct. Okay, now the homework for you would be to try to understand what did it do when the two conditions were put in series and not contemporaneously. Okay, I have an idea, but let's forget about it. Today we have to try to finalize this. Okay, and now let me see a plot of the vector probe, type equal line. And let's see what we get. You see, this is the bell that I depicted yesterday on the blackboard. Please have a look at the ordinates. You see that this is nothing meaningful because I didn't divide for 10,000, so it's not relative frequency, just the number of counts in each of the beams. And if I want to divide for the number of observations to get the relative frequency, now here I get the relative frequency, but still you see that the area behind this density, this distribution, it's not one, it's more than one. You see, because if you look here at from 15 to 5, basically, you have a distance of 10, and 10 multiplied by 0.15 is greater than 1, basically. If I want to get the density, I have to divide the relative frequency by the width of the interval. And then, let me see what happens. Okay, let me go back to the previous equation, sorry. Okay. So, because I think we need to compute this area, let me see, is... because I said it's greater than 1 and it is lower than 1. Okay, this area is lower than 1. Instead, if I divide for the width of the interval and I plot again, now the area, sorry. Here, let me plot. the area should be 1. And let me see, because it's 0.3, should be, it's not so clear, but should be, now the area should be 1. Because it's not easy to make an estimate, but let me say it's like a triangle, so the base is 10. The height is 0.3 divided by 2 should be 10, 3 divided by 2 5, should be around 1. Of course, this is not strictly correct, because there is approximation. Okay, now let me introduce to you a very simplest way